So, hello everyone, and welcome to this week's JHU-IIT Delhi collaborative seminar, Smart Seminar series. In our seminar today, we are very pleased to host Shailesh Garg, who is a Ph.D. scholar at the Indian Institute of Technology, Delhi. He is advised by Professor Shovik Chakraborty, and he's working at the intersection of computational mechanics and deep learning. Before joining as a PhD student at the IIT Delhi, he graduated from IIT Guwahati with a specialization in structural engineering, completing his master's, and he got his bachelor's degree from Punjab University in civil engineering. His current research focuses on developing neuroscience-inspired, sustainable, and energy-efficient deep learning algorithms. And with that brief introduction, I leave the floor to you, Shailesh. It's all yours.
Yes, ma'am. So thank you for the introduction and hello everyone. I hope everyone is having a good day. I'm Shailesh Garg and today I will be giving my talk on the topic Neuroscience-Inspired Deep Learning Algorithms for Computational Mechanics. So I hope my screen is visible to everyone.
Yes.
Just someone confirm.
Yes, it works.
Yeah, well, hope. Okay. So I'll start with some motivation on the topic and some background on the topic, and then I will introduce the variable spiking neuron that we have developed. And subsequently, I will discuss the frameworks that utilize that said variable spiking neuron for computational mechanics and scientific machine learning tasks. Okay. So in today's time, artificial intelligence and neural network algorithms have virtually crossed that initiation threshold, and they are being widely used across all fields, right? So from aerospace to medicine to topology optimization, weather, climate forecasting, anywhere. So we will see extensive use of deep learning and neural network applications. And as the models that are used scale up, right, they tackle bigger and bigger problems. The parameters that require training also increase, and subsequently the computations that are required to get the desired results also increase. Now, with these increased computations, what happens is that the energy consumption, the energy required to train these models, to do inference, to predict the required outputs, the energy required also increases subsequently, right? Now, because of this high energy requirement, the AI algorithms that we use today, they are not sustainable, right? And looking at the state of the current the environment, right? The sustainability is a big concern in today's time. And even if we don't look at these societal problems, then practically as well, implementing these AI algorithms in field, in embedded or edge devices is no longer suitable if the energy consumption, if the power that they require is exponentially high, right? Now we see that our mobile phones mostly uses AI agents or AI algorithms to perform various tasks, but we don't keep them plugged in for longer periods, right? For continuous amount of times. So the thing there is that the most of the computation that is happening, that is happening back at the server farm and not in the mobile phone itself. So the mobile basically acts for the most part as an input-output device, and the actual computation is occurring on the server. So if you want that everything should happen on the end device only, so then we require energy-efficient algorithms that can perform very well with a limited amount of energy. So before delving deeper into artificial side of things, let us see how natural intelligence works, right? So human brain or animal brain in general, it works tremendously well with a very low energy budget. So it is widely accepted that energy budget of human brain is around 20 watts. And within this energy budget only, it performs very well in noisy environments. It is able to perform online learning. It accepts continuous information, and we are able to perform multiple small tasks while focusing on one primary task, right? And it has been observed that the information flow within our nervous system, within our brain, is sparse. It is not a continuous information flow. Compare this to deep learning algorithms, where, as I just shown you, that as the deep learning algorithms scale up, their energy requirements can go up to several megawatts, right? So comparing it to the brain, human brain, the difference is quite evident, right? And the main reason why deep learning algorithms are consuming so much energy is that right now the artificial neuron that we use within our deep learning algorithms, they fire continuously, and because they are firing continuously, the number of computations that are required increase, and subsequently the energy requirement also increases, right? So the goal here is to develop green AI that is energy efficient, accurate, and that can generalize well as well, right? So not only should it be energy efficient, but it should be able to uh, produce accurate results. So let us see how biological neuron does things, and then we will try to model it so that we can implement similar principles in our deep learning algorithms, right? So let me use the pointer. Okay. So this is a schematic for a biological neuron. If you will see, it has a main body connected to a long tail, and on this main body there are dendrites and synapses available. So these dendrites, through these dendrites and synapses, this biological neuron is connected to other several hundreds of biological neurons, which are providing it information, right? So what this neuron does is that it collects the incoming information, and once that information crosses a certain threshold, then it fires an output spike, which is then transferred to other connected neurons. So if you will see, if I were to plot the graph of this incoming information and outgoing information, you will see that the incoming information is accumulated over time, right? And once it crosses a threshold, you will observe a spike, and after that spike, that voltage of this biological neuron will again reset, and the whole process will start from scratch. So basically, biological neurons are not always active. So as and when it receives input, it is not giving you the output. It collects the inputs, stores them, and once only passes them forward only when a certain threshold is crossed, right? So there is a mathematical model for this biological neuron, which is perhaps the most biologically plausible model, which is Hodgkin-Huxley model, and it accounts for the various ion differences that are generated. Sodium ions, potassium ions are there, right? Various channels, gates that are used to collect, store the information and pass it forward. So it accounts for various things, and if you will see, if you were to plot the graph of this, you will see that incoming information is there, and then it spikes and resets, and again the process repeats, right? But as I just said, that this is quite an involved mathematical model. So there exists a simplified model as well, which is called as Leaky Integrate-and-Fire model. So the idea here is again same. So ZT is the incoming information. Z is your incoming information. It is stored in your memory M, memory variable M. And once this memory crosses a certain threshold, you will observe a spike. And if it doesn't cross a certain threshold, then you will observe no information flow is there, right? So similarly, in this plot, you will see that information is incoming. It is not crossing the threshold, and only when it crosses the threshold, you see the output spike. So this is the main advantage of biological neuron, of using mathematical models based on biological neuron, that you get to have sparse communication even when you have continuous information flow incoming information flow, right? Now, how are these models used in deep learning and artificial neural networks? So this inner portion is perhaps a generic diagram of any neural network algorithm. So what happens is that these spiking neurons are used in place of continuous activation, or continuous activation sigma. So as I told earlier, that continuous firing of spike of artificial neurons is the main issue, right? We want to stop that from happening. So instead of using your continuous activations, we tend to use these spiking neurons, and in this particular case, live neuron, right? And apart from this, there is an encoder and decoder sitting as well. So why are these there? So because live neurons, as I showed here, they have a time dimension as well, which I will be referring to as spike time steps. They have a time dimension as well. So this gives us the opportunity to present our incoming information in the form of spike trains, So that is why there is an encoder which will encode your incoming information, and then there is a decoder which will decode these spike trains to obtain again real values, right? And in the literature, you will see that using live neurons, people have been able to show that spiking neural networks are tremendously energy efficient. So you will see that normal CNN, where it is consuming 8.94 watts for certain tasks, SNN, spiking neural network, is only consuming 0.064 watts. So using live neurons, people have shown that spiking neural networks are tremendously energy efficient. Now I will tackle a few components of these spiking neural networks before moving on to the variable spiking neuron part, right? So as I just showed that the incoming information can be encoded in the form of spike trains. So how can you encode it actually? So there are two techniques available, which two popular techniques available. One is the time encoding and the other one is the rate encoding. So in time encoding, what you do is that the time at which your spikes are occurring, so those are of great concern, and they govern how the information is encoded, right? And in rate encoding, the idea is that instead of when the spike is occurring, the total number of spikes is our main concern. So let us suppose we give each spike weight of 1. So this information could represent a real number equal to 5 because there are 5 spikes, right? That will depend on how you are defining your average. But in rate encoding, the idea is that the number of spikes are of main concern, and in time encoding, the idea is that the time at which spikes are occurring is our main concern, right? And time encoding is perhaps more biologically plausible because it is more energy efficient. And as we know that our brain works on very meager energy budget, right? So if it were to employ rate encoding, the energy required in computations will be absolutely high. So that is not biologically plausible, but it has been seen that some portion of brains tend to use rate encoding as well because there the information is averaged out in some sense. Then there are in the literature, there are hybrid encoding techniques available as well, which take help of both the time at which spikes are occurring and the frequency of spikes as well. And one other option is that at each spike time, you give the inputs directly, right? So for example, if I go back, so you pass the same real number which you want to give as input at each spike time step, right? And let the new spiking neural network or any neural network figure out on its own that how to process that information. So we have observed that direct inputs tend to work better for regression tasks, but that I will come later on. And as I said that brain prefers time encoding for the most part, but some portion of brains also rely on rate encoding as well, right? So now, how is live neuron energy efficient? So these spiking neural networks are basically not designed for GPU type architectures. They are designed for event-driven hardwares. Event-driven hardware means that the computation will take place only when there is some relevant information. If there is no spike, if there is no relevant information, the computation won't occur. So in the case of artificial neuron, if you will see, when we have a vector populated with all real values, so then you will have to do this multiplication operation for each of those values, and subsequently you will need to sum them and add the bias, and then only you will get the neuron output, right? But in case of live neuron, what is happening is that because spikes are only occurring at some places, not every spike time step, spikes are only occurring at some places. So you get to avoid a lot of multiplication operations, right? And even when spike occurs, you don't need to multiply it with anything because its magnitude is 1. It is a binary spike, either 1 or 0, right? So because its magnitude is 1, so you don't need to do any multiplication. You just simply sum the weight and add the bias and get your output. So basically in synaptic operations, when you are using live neurons, first of all, you get to eliminate the multiplication operation. And second thing is that you only have to do these operations, that you get the neuron state, you do the addition, you write the neuron state back only when spikes are occurring, right? Otherwise, there is no required. Okay. So that is why we, in the subsequent slides as well, when I will talk about energy efficiency, I will talk about the spiking activity of variable spiking neuron or live neuron, because spiking activity is a surrogate measure for the energy consumption. Less number of spikes, less number of computation required, and subsequently less amount of energy expended, right? Now, in scientific machine learning, we deal with a lot of we deal with a lot of regression tasks, right? So let us see the performance of live neurons in regression tasks. So this is a simple example: y is equal to 10 to the power minus 5, 5x square plus 200x, a simple nonlinear relationship between x and y. And if we see the performance of live neuron when using a single spike time step is absolutely worse. And even when using 5 spike time steps, the performance is not that good. It is not a very complex relationship, so it should be able to map it, learn it very well. But even with 5 spike time steps, the performance is not that good, right? So live neuron or live neuron based spiking neural networks, they fail to perform well for regression tasks. And although accuracy increases with spike time steps, if we were to take more spike time steps, there is more opportunity for spiking activity. If there is more opportunity for spiking activity, we will observe more computations required, right? So that ultimately defeats the purpose. So possible reasons for underperforming of live neurons are, first of all, it is a simplified model, right? Then there is gradient computations and optimizer involved as well. And one of the possible reasons is that it performs only binary communication. It will either give you a 0, which is non-spike event, or it will give you a 1, which is your spiking event, right? So what we did was that went back to neuroscience to see that how else is brain passing information, or how else is brain doing computations, right? So in brain, in different types of neurons, you will see that there are graded spikes used as well, right? So it is not always that brain uses binary spikes only. Often brain uses graded spikes as well. So what we did was that we took the live neuron model and modified it such that in the event of spike, in the event of spike, the input that resulted in the spike, we pass that forward after using some continuous activation. So I will repeat again. So let us suppose this ZT is your input, right? So it is stored in your memory. That memory is checked against the threshold, right? In case of spike, what you will do is that you will pass that incoming input ZT. After passing it through a continuous activation, that will be your final output, right? So the spiking activity is no longer binary. It is now either 0, which is your non-spike event, or some uh, some real number which will depend on sigma z, right? So we call this neuron as variable spiking neuron. Why variable? Because it can generate spikes of variable amplitudes, right? Not 0 and 1. It is actually 0 and real number. So now, those who are familiar with training neural networks, they know that ultimately we need to do gradient computation through this neuron model, right? And because there is a discontinuity involved here, there's a heaviside function involved here, we cannot find gradients in a normal way, right? So we need to do some trickery for that if we want to train our if we want to train our variable spiking neural networks. So what we do is that we approximate this heaviside function using a smooth function, and then instead of using the gradients of this heaviside function directly, we use the gradients of this smooth function during our backpropagation, right? So just to show you an example, in the forward pass you use your normal heaviside function, so inputs are incoming, right, and you get the desired output. But during the backward pass, instead of using the gradient of heaviside function, what you do is that you use the gradient of your smooth function, and using that you find the required gradients. Okay. Now, is VSN energy efficient? So first of all, I should mention that because the spikes are non-binary now, so that multiplication operation comes back into picture, right? But still it is more energy efficient than using, I would say, an artificial neuron, because still the number of spikes that are generated, the ratio of spikes that are generated, still they will be able to reduce all these computations that are required, right? You don't have to do the multiplication and addition operation all the time. Only when a real number spike is generated, then only you need to do the required computations. And in our studies, we saw that based on the spiking activity, if the ratio of energy required based on 100% observed spiking activity to based on 100% spiking activity was almost 0.15 in some cases, as low as 0.11, and 0.63 for fashion MNIST dataset, right? So let us now compare because our main motivation was what? That our spiking neuron should work for regression tasks, right? The new spiking neuron that we have developed, it should work for regression tasks. So let us see the performance of live neuron and the variable spiking neuron. These two plots I had shown you earlier only, that live neuron is not able to perform well for regression tasks. But when we are using variable spiking neuron, with only a single spike time step, you will see that we got very good results, right? In the same task with only a single spike time step, the predicted output is very closely following the ground truth. And we ran multiple case studies for multiple examples for benchmarking this variable spiking neuron, and we saw that in classification, accuracy of artificial neuron, live neuron, and variable spiking neuron were all comparable. So if you will see against 98%, you are getting 98% and 97%. So in classification task, performance was expected that live neuron will also perform very good. But in regression tasks, if you will see, the performance of this variable spiking neuron is much better than the performance of live neuron. And in this particular task, for example, it also outperformed artificial neuron, but still it is in the similar range only. The key factor here is that it outperformed live neuron by several magnitudes, right? So that is the main advantage here. Now the question is that these data sets, for example, these were very generic data set. There was only a uh, elementary nonlinear relationship between the inputs and outputs, right? So the thing is that we should explore that whether these variable spiking neurons can actually be used for scientific machine learning tasks, right? So in our in the first framework that I will show you, we used the this variable spiking neurons within graph neural network architectures. And the idea was again simple, that in the message passing layers, instead of your normal continuous activations, you use the variable spiking neurons. And now the node features will only be non-zero if the incoming information crosses the certain threshold. If it doesn't crosses the certain threshold, then your node features will be zero, right? So the first example that we took was learning mechanical properties of alpha titanium polycrystals, right? So based on crystallographic textures of these material, we tried to predict stiffness and yield strength. And the architecture was something like this. SageConf message passing layers were used in this. And we tried two different variations of architecture. One in which all the activations were replaced by variable spiking neurons, and one in which only first three activations were replaced by variable spiking neuron. Look, the idea is that we want a more energy efficient architecture, but we want to retain accuracy as well, right? So it is sometimes preferred that instead of replacing all the activations by your spiking neuron or variable spiking neuron, you replace only a few activations with your variable spiking neuron, and let the remaining ones be same, so that you can maintain a balance between the energy efficiency and the uh, accuracy of your architecture. Okay, so these were the results obtained. So if you will see this HVS-GNN, it is basically hybrid variable spiking graph neural network. It should have been variable spiking only, not hybrid, but anyway. So this VSGNN1 and VSGNN2 are the two types of architecture that I showed you. One in which all the spiking layers are replaced, and one in which only three spiking layers are replaced. So if you will see that variable spiking neurons performed very well in predicting this stiffness and yield strength, both in within distribution. This evaluation one is within distribution, and evaluation two is out of distribution prediction, right? Both within distribution and out of distribution, the results produced are very close to what you get when you are using vanilla artificial neural network, and better than what you are getting when using live neurons. And as for spiking activity, you will see that spiking activity is well below 60% in all different layers of your architecture. Okay. So the another example that we took was prediction of magnetostriction in polycrystalline material. So again, based on this microstructure of your polycrystalline material, we predicted this magnetostriction property. And if you will see, Two types of architectures were used. One in which all the layers were replaced with spiking neurons, and other one in which only of certain layers were replaced by spiking neurons. And in this example as well, the variable spiking graph neural network outperformed the live neuron, the graph neural network which used live neuron. And again, for this particular example, it outperformed artificial graph neural network as well. So in artificial graph neural network, you are getting error of 9.67 into 10 to the power minus 9, whereas in variable spiking graph neural network, you are getting an error of 4.29 into 10 to the power minus 9, right? And spiking activity, if you will see, only a maximum of 20% spiking activity you are getting. Otherwise, it is well below 100%, right? So after this, once we had tested this spiking neuron for graph neural networks, we now wanted to see whether it will perform well in a more complex architecture like neural operators, right? So we implemented variable spiking wavelet neural operator. So before moving on to that, I will just very quickly discuss what is wavelet neural operator. So those of you who are not familiar with neural operator architectures. So the idea in neural operator architectures is that you learn mapping between two different function spaces, and wavelet neural operator is a kernel-based neural operator that exploits wavelet transformation to learn this mapping, right? So let us suppose you have a partial differential equation with some input function A and you have your output U, and you want to learn the mapping between the two. So how it will do is that wavelet neural operator will accept your input function A along with the grid on which it is discretized. Then it first of all it does some lifting transformation, so that these are two features only, right? So we increase the number of features that we have to, let us suppose, 10 or 20 based on your architecture, right? And then that information is passed through several iterative layers, and once you after the last iterative layer, you then again downgrade, you project that increased number of features to get the desired number of features as your output, right? And within this wavelet blocks, what is happening is that your input, you pass it through, you do wavelet transform of this input, you learn the coefficients that you obtain, and then you do the inverse wavelet transform, and you also add this input after passing through a convolution layer, you obtain the final sum, and that is your, after passing it through a continuous activation, that is your final output, right? And in variable spiking WNO, what we do is that we replace this activation with our variable spiking neuron, right? But the idea is that the super resolution property of this wavelet neural operator should not be disturbed, because that is one of the key properties of your neural operator architectures. So if we were to see the information flow in WNO architecture, if we were to use normal continuous activation, you will see a matrix. If our inputs and outputs are 2D, for example, you will see a matrix populated with real number values. If we were to use live neuron based architecture, then the matrices that you will see will either have 0 or 1s, right? And in our case, in our variable spiking WNO architecture, we see matrices populated with either zeros, which are non-spiking events, or some real numbers, right? And here, although I have shown multiple matrices, but if you use only a single spike time step, for example, you will see only a single matrix with populated with either non-spiking events or real values, right? So we tested this architecture for multiple different PDs, for Burgess, Ellen Kahan, and Darcy on rectangular domain and triangular domain. And if you will see, again, the results are similar to what was observed in variable spiking graph neural networks, that the results produced using variable spiking variant of WNO are much closer to the vanilla WNO, whereas the results produced using live neuron are not that good, right? So if you will see, 1.88% error is observed in normal vanilla WNO, whereas in live versions, the error is as high as 45%, right? And in our variable spiking variant, the error is only 2.87% or 2.7%. So what is this L and GALU, I should mention? So within variable spiking neuron, I showed you there is sigma Z involved, right? So that sigma, if this L represents that sigma is a linear activation, and this GALU represents that sigma is a GALU activation, right? And from the plots as well, from the contour plots as well, you will see that the predictions obtained using variable spiking variant of WNO are close to ground truth. They give a very good approximation, and the absolute error observed is quite less, right? Now, for the spiking activity, you will observe that the spiking activity observed in various examples is again much less than 100%, although at some places it went as high as 80%, almost 75-80%, but still it is much less than 100%, right? So the question now is that can we further bring down the spiking activity? Now to do that, what we did was that we introduced one spiking loss function. So in your normal neural network, what happens is that you only penalize the difference between the predicted output and the true label, right? But in this loss function, apart from that predicted output and true label penalization, we also penalize the spiking activity of your neuron. Okay. And if you will see, these orange ones and the green ones are the spiking activity observed after using the spiking loss function. So you will see that there is drastic reduction in spiking activity at some places. For example, in this particular case, it reduced from almost 55% to around 12%, right? And in this example as well, where the spiking activity was approaching 80%, it got down to 45-40%, right? Now, because the spiking activity has reduced, the flow of information has reduced, right? So there is obviously going to be increase in error observed, right? But if you will see, the increase in error is hardly appreciable, like 0.25%, 0.4%. I think it went as high as 0.6% in this case, right? So by sacrificing only a little bit of accuracy, you are able to reduce the spiking activity by a great amount when using the spiking loss function. So this was all about the variable spiking WNO. Now, as I discussed that because after reducing the spiking activity, you are curtailing the flow of information, right? So because the information is curtailed, the flow of information is curtailed, there is going to be accuracy loss. So it becomes essential that you estimate the predictive uncertainty, the uncertainty associated with the predictions of variable spiking neural networks or variable spiking neural operators, right? So for that purpose, we developed conformal prediction within variable spiking WNO. The idea in conformal prediction is that you obtain some initial uncertainty estimate using whatever algorithm you want. You can have a Bayesian neural network. You can use deterministic methods like ensemble method, randomized prior, whatever method you want to use. You obtain some form of initial uncertainty and then calibrate that uncertainty estimates using your split conformal prediction, right? So in our case, for base uncertainty quantification, we used randomized prior networks. Basically, we used RPWNO, randomized prior wavelet neural operator. And the idea in it is that when you are training your neural network, you also augment it with some with output of another neural network with fixed weights, right? And you train multiple copies of that network, right? So you will obtain multiple outputs corresponding to same input, and then by combining these outputs, you can obtain the mean output and the standard deviation observed, right? So this mean and standard deviation will act as your initial uncertainty estimate, right? So we will get some type of confidence interval where we have the mean value and the associated standard deviation, right? The advantage of using randomized prior operator as our initial estimate is that it is parallelizable because it is trained, because these copies does not have anything to do with one another, right? Only after the outputs are obtained do we combine them. So we can train them in parallel, right? And it is able to capture uncertainty due to surrogate gradient and the optimizer. One other advantage that I forgot to mention here is that despite being a deterministic method, it can account for prior information as well, right? As I told you that you augment your outputs with some another output of a neural network with fixed weight and biases, right? So once you obtain this initial uncertainty estimate, what we do is that we see where our true values are lying for the calibration dataset. So For our calibration data set, let us, for example, in this case, I have shown 4 samples. So for this one and this one, the true value is lying within your confidence interval, but these two, the true value is beyond the confidence interval, right? So for each sample, you obtain some score function based on these true values and your initial uncertainty estimates. And then using those score functions, you obtain the parameter Q, and then this Q will calibrate your this uncertainty bounds to so that the true values always lie within the uncertainty estimates. Now, although in this figure it looks like it is simply increasing the uncertainty bound, that is not always true. It may happen that the uncertainty bound actually shrinks if the Q value is less than 1, and that is entirely possible. If your initial uncertainty estimate was too liberal, it was too it gave you bounds that are too big, right? So it may happen that ultimately the bounds that you get are reduced as well, right? So it is not that you are mindlessly increasing the bound size to include the true value within your uncertainty bounds. Right? So we again performed multiple examples to test the performance of conformal VSWNO, but here I have shown results for two Burger's equation and Darcy equation. So if you will see that when using conformalized version of WNO and variable spiking WNO, we got the desired coverage at all the grid points. So in this example, the grid was discretized at 1024 points, and for Darcy, it was discretized at 700 to 7225 points. And at all different points, we got the desired coverage of 95%, right? And similarly, this plot shows the same thing again, that when you are using normal randomized pair VSWNO, at some points, at some grid locations, you are not getting the desired coverage. But when you conformalize it, when you calibrate it using split conformal prediction, you get the desired coverage at all points. And the mean prediction as well, because it is a WNO architecture, it is trained using ensemble method, right? So obviously the mean prediction matches with the ground truth very well. Now, as I was saying, that super resolution is a big part of neural operator architectures. So our calibrated uncertainty bounds, these bounds should work well for our should work well for super resolution cases as well. So what we do is that because our parameter Q is dependent on the calibration on the grid which was in the calibration data set, right? Which we so let us suppose calibration data set grid size was 10 cross 10, right? So what you will do is that using Gaussian process regression, you will map these xi's to these qy's to your grid locations, and then so let us suppose your new grid is 20 by 20. So then you will predict these conformal parameters q on the new grid location, and this whole process is based on Gaussian process regression, right? And if you will see, when using conformalized RP, randomized prior variable specking WNO for super resolution, initially in super resolution case, we were not getting a very good coverage at all. At a lot of points, we were not getting 95% coverage, but after using CRP VSWNO, the coverage obtained was very good for several grid locations, although at some grid locations we did not get 95% coverage, but still much better than what we obtained previously, right? So this was all about the architectures that I wanted to discuss today. Now going forward, how we can improve the variable spiking neuron is that we can first of all develop a better neuron model, in the sense that it can take into account spike time dynamics very well. So because there is a extra time dimension available with us, right? So we can make use of that in a much better way. And as we saw in the results, although they were very close to when using continuous activations, they can still improve further, right? And improved efficiency in terms of energy. Why? Because we are dealing with non-graded spikes, right? So that multiplication operation, as I showed you, it comes back into picture, right? So we can modify the neuron model somehow that either the spiking activity reduces further, or somehow we get rid of that multiplication operation so that we can get more energy efficient architectures, right? And then optimizers, because we are using surrogate gradients, right now the surrogate gradient based backpropagation is being used. So maybe we can look at optimizers which don't require gradients for updating your weights and biases, right? Or maybe we can use some better estimates for gradients other than using a surrogate function, right? Maybe we can come up with some estimates that don't require use of surrogate gradients at all, right? And lastly, the main thing is that to validate all these results, right now we are using spiking activity as a surrogate measure for your energy efficiency, right? So we can maybe you implement this whole thing on neuromorphic hardware and actually get empirical results for energy efficiency, right? So that will again strengthen a lot of the claims that have been made, right? So these are the key references for various works that have been shown in this work in this PPT. And thank you so much. I think I ended much before my time, but this was all from my side. So I will now take any questions that you may have.
Thank you, Shailesh, for this very nice presentation. So yeah, if anybody has any question for Shailesh. Yeah, I see your hands up. Yeah, Dibyajyoti, please go ahead.
Uh, Hi, Shailesh. Thanks for the wonderful talk. I had a few questions. I think you would have covered it, but just to get some clarity. You mentioned about usage of a sigma activation function in the VSN framework, right?
Yeah.
So how critical is the choice of a particular form of sigma in that case? Like,
So
can you use any sigma or?
So look, in normal neural network architectures as well, the choice of sigma can significantly affect your performance, right? So in WNO, for example, we get good performance with GALU activation, right? Normally, GALU activation tends to perform much better than your normal ReLU activation, or there is one MISH activation as well, I think, that also performs well. But similar principles apply in case of variable spiking neuron as well. So if you were to take a linear activation or ReLU activation, it might not perform that well compared against using ReLU activation. So similar principles, how you will decide the choice of activation in your normal neural network architectures, same thing applies here as well.
Okay, okay. And my next question is, did you also get a chance to compare your VSN with, let's say, a feed-forward neural network where you have a very aggressive dropout rate? Because I can imagine that when you are implementing dropout, you are cutting a few connections to the neurons, and that essentially means that they won't fire at all. Did you just have a comparison with them? Like have a very high dropout ratio and then just see the energy efficiency and accuracy.
No, we did not do comparison with dropout networks, but I don't like if we are using dropout, right? So that accuracy, we did not do actually the comparisons with dropout augmented networks. So that is something we can look into, definitely.
Okay, okay. And just final question which I have is you mentioned about adding adding a constraint which penalizes the spiking activity also. Like you had a spiking loss term
Right, right,
in
right.
your yeah. So how do you actually back propagate through that term? Because the
How
spiking
do you actually?
activity back propagate through the spiking loss term.
Okay, so it is basically some of your output obtained at like before you pass your input through activation in that step, right?
Yeah.
So it is simply a summation used to compute the spiking activity. Right now, I don't have any equations for you. Let me see if I can show you that. Yeah. So after this step, whatever metrics you obtain, right, you simply sum that to get the spiking activity and then you use it in the loss function. I understand what you are trying to ask, that how you're back propagating through it, but
Yeah.
that right now I don't have anything to say, like show you for that particular question.
No, I was actually wondering, since you have something like a delta function uh, for
Sorry,
the spiking activity, uh, I was just wondering how
can you
do
repeat?
you
So Shailesh,
so
I think if I may rephrase,
yeah,
I think so. What Divya is asking is that if he's actually just thinking that since the input that you're giving is actually a spike, which is a direct delta spike, right? So it's a discontinuous. So therefore, his our question is that if you're back propagating, is that discontinuity creating a problem?
yeah, exactly.
Continuity to ultimately we use surrogate gradients na, for that. Like,
Ah,
and as far as inputs are concerned, in our architectures we don't use encoded inputs. We directly supply them. Like, even if we were to use multiple spike time steps, right now we are not using multiple spike time steps. But even if we were to use multiple spike time steps, we give direct inputs only, right? We let the network figure out thresholds and leakage parameter so on its own. So instead of supplying like previously encoded inputs to the network directly.
I see. Okay, okay, okay. Thank you.
thanks, Divya. I think. So maybe I'll ask a few questions because Divya actually kind of stole one of my questions, which was the second question regarding but yeah, anyways, let me rephrase it. So the dropout question that he raised, I was also thinking like maybe it would be nice to compare it. What is the energy efficiency of a spiking neural network with, let's say, a neural network where some of the weights are zero? For example, if you are considering a network such as a dropout or something of a network which has um, a Bayesian, a spike and slab kind of a prior on the weight. So it would either be zero or be non-zero, some kind of thing like that. Where if there's an extreme sparsification of a network, then the energy efficiency. So I believe that in your case, the inputs are actually coming in as spikes, whereas for a dropout or a spiking kind of a or a spike and slab affected neural network, that would be like the weights are going to be zero. So in which way would that be a correct comparison? So one of the questions was that. So like, what do you think?
Look, and my point here is only that if we were to talk about dropout, for example, right? So you can
Mhm.
implement dropout within spiking neural networks as well. It is not that spiking neural networks will not support dropout. If artificial neural network is getting good accuracy with dropout embedded in it, so you can use instead of continuous activations, you replace them with variable spiking neurons, and you retain the dropout layer.
No,
We
the
can
issue is not that much the because the prime thing that why you're working with a spiking neural network is to achieve energy efficiency
Hmm.
without relaxing the without actually going down on accuracy. So therefore, the question that uh, does a neuron network a neuron having a zero weight would lead to an energy efficiency, or it is has to be the case that where the input has to be encoded in the form of a direct delta function like the spikes?
No, I think with zero weights as well, you will obtain energy efficiency, because ultimately, if your weight is zero, you don't have to do that
Right.
computation,
In which case,
right?
I believe
So,
that a comparison with a very extremely sparsified dropout based ANN would also be a suitable comparison, right? I think
true,
that was
true,
what
true.
Divya's question was.
Yes, sir.
So, another question that I had, which was basically that since you are now using the different surrogate based gradient while back propagating for these kind of networks, right? Wouldn't
Yes.
that create a bias in the optimization? Because you
Bias in the
have
sense.
in a bias in the sense that uh, well, whenever you create a surrogate, right, you do kind of know that that surrogate is not exactly the model, but it is trying to mimic as close as possible to that thing that you want. And therefore, there will be some kind of a bias, some small bias, maybe very small, but there is
Mhm.
a bias. Since you're using it for the forward pass, you're using a different model, and for the backward pass, you're using a different model. So I would expect that there will be a certain amount of bias. Did you kind of see that what kind of surrogates would actually create how much bias, a study on that one or something of that sort?
We did not study particularly the bias that is created, but accuracy obviously is affected by using different surrogate functions. So if you are to take a very good approximation of heaviside, right, then your network tends to perform much better. But I should mention one thing here, that if you were to take a very good copy of heaviside function, right, then what happens is that because that working range of that gradient reduces, it is non-zero at very few places, right? So then also it creates a issue in the training of your neural network. So that surrogate gradient cannot be very close to heaviside function, and also it cannot be very far away from heaviside function that it gives you complete garbage training at, right? So there has to be a very fine balance maintained while choosing your surrogate function.
I see.
You cannot go exact direct delta. You cannot go
Right.
very far away from direct delta. It has to be somewhere in between.
So my last question is regarding this, the idea that in what I understand from the spiking neural network is essentially that you are actually kind of changing the information that you would have continuous to actually spikes, right? This information is being
Yes.
fed in the inputs. Is that correct?
Inputs like
I
in
mean, so
input of
basically,
neural network.
yeah. So a neural network will also take some inputs. So where is this? So how are you actually encoding these spikes? And so you're taking the input, whatever the input is, and then you're encoding it as spikes and then sending it to the neural network. Is that correct?
So there can be two types of inputs. Let me clarify. So there can be two types of input. One is that your inputs originally are in the form of spikes. So for example, from event-driven cameras are available, right?
Right.
So information that comes from event-driven cameras are already in the form of spikes. So those
Right.
inputs you can directly pass on to spiking neural network without any changing, right? But let us suppose you are training your neural network and your input is 5 and your output is, let us suppose, 2. In that particular case, you want to use spiking neural network. What to do then, right? So what you will
Right.
do is that you can directly supply 5 as input to your spiking neural network. There is no issue in that. It works very well, right? It will figure out on its own in subsequent layers that how spike train should look like, right? Maybe
I
not,
see.
maybe there is no spike train in the input, but it will encode that information automatically on its own by changing its parameters, weights, bias, threshold, leakage parameter, whatever it is, right? Or what you can do is that you can transform your data prior from 5 to a spike train and then provide that spike train to your spiking neural network. Okay, so
Right.
there are both kind of three kinds of options available. Either you collect data from a sensor which already gives you spikes, right?
Which is
Or
usually
you
not the case.
which is usually not the case, true.
Right.
Or you provide your data directly and let the neural network figure out on its own that how to process that information, or you convert it into spikes prior to supplying it to neural network, and then neural network can proceed however it wants later on.
So
And
from
to
this, yeah. Please
yeah,
go ahead.
I was just saying that to encode your information, you can, as I showed you, that you can use different techniques that are available. Time encoding is there, rate encoding is there, or some hybrid form of those two, right? So that is your option choice.
So in totality, would it be a good statement to make that to convert these inputs, which are in general not in the form of spikes, to spikes which are kind of because you had been talking about the rate at which you would try to send the spikes as well as the number of the time difference between each spike, right? So that itself is an optimization on its own, right? So because that will actually also affect the regression results that you have shown. So would it be
Absolutely.
so is it a good point to say that a spiking neural network in right now the phase that you show is also can be fragile because the encoding of these spikes would also affect the results. So you have to also
Definitely.
find, okay. So,
So
okay, I see.
yeah. So the thing is, that is why we started supplying direct inputs, right? Instead of doing rate encodings. Because what happens is that in rate encoding, if you were to use 10 spike time steps only, right? Within 10 spike time steps, only so much information you can encode. If your input is if your inputs are like this, 0.0071, 0.0072, right? The difference is of 0.0001, right? So that kind of difference, to create that kind of difference in your encoded information, you will require a huge number of spike time steps, right? So to avoid that problem, what we saw was that we pass the information directly. We let the neural network figure out on its own. So as you said, that it can be an optimization problem, right? So that neural network will optimize itself, its parameters on its own, to get maximum accuracy and maximum energy efficiency, right? So that is why using rate encoding is harmful in that way only. That is why I said brain also uses maybe time encoding, because time encoding still requires less number of spike time steps. But rate encoding, if for example, it will require huge number of spike time steps. And coming up with a good encoding technique is also one of a major challenges,
Challenges.
right? So
So
that
Shailesh, so
yes.
maybe sorry to interrupt you, but in general, like so the actual effectiveness of these neural networks would probably only be realizable once you use it on a neuromorphic hardware, right? Only then you can actually show the efficiency that you are actually talking about, right?
True, true.
Okay.
Because in neuromorphic hardwares, first of all, we will get to see practically how much energy is being saved, right? They will be more energy efficient, that is without a doubt. Because even if you were to run artificial neural network architecture on neuromorphic hardware, you will see some form of energy efficiency compared to when using GPUs, right? So they are more energy efficient without a doubt. And when you are giving sparse information, they will be obviously more, because they are event driven, they will have to do less computations and energy efficiency will be more, right? But by how much more, that to quantify that, we will have to run it on neuromorphic hardware. And the current stage of neuromorphic hardwares, the where they are today, right? So they used integer encoding and integer values only, right? Integer maths they use. So all those things will also lead to some form of accuracy loss, right? But to quantify how much, we will have to run these algorithms on neuromorphic hardware.
I see. Okay. So anybody else has any other question from the audience? If not, then thank you so much, Shailesh, for the wonderful talk. Souvik, you want to announce a few things? Souvik, if you're there.
No, I think next week, I think Professor Subhan Day is speaking. So
Right, yeah. So we'll have
that will
Shubhan
be-
Dey speaking from University of Northern
and the
Arizona.
week after that, Professor Ognimitra Dasgupta, sorry, Dr. Ognimitra Dasgupta will probably speak. So these two are the updates for next 2 weeks.
Right. So
And
stay
the
tuned.
week,
We'll see
and
you
then,
again.
yeah, Elias is there. Professor Elias
Right.
Williams will speak. So we have 3 exciting talks coming up in next 3 weeks.
Yeah. So stay tuned with our LinkedIn updates and we'll actually catch you again next week. Bye, everyone.